Hey guys, this is JB Mon from Planning Seeds Tutoring. In this video, we'll be talking about the basics of circuits. Don't forget to use my referral code JBMon20 to get 10% off on your next tutoring package. So let's get started. A circuit is just a path through which electrons travel. So in general, we're going to be seeing like a diagram which kind of shows how electrons travel through, the pathway through which electrons travel through. All right. So Ohm's law is one of the best describers of how the circuit itself works. I mean, it is the best description. And it describes voltage, current, and resistance, all of which we're going to talk about in a minute. Simply speaking, Ohm's law is a mathematical equation which just states V equals IR, where V is the voltage of the system, I is the current, and R is the resistance. The voltage, which as you can see is denoted V, has units volts, which is also denoted with the letter V. And this is pretty much the amount of energy, simply speaking, that pushes 1 unit of charge. The current of a system in units of amps, amperes, or amps, which is denoted with just that. Either you might either write down just amps, or you can write it down as with the letter A, with the capital letter A. And this is the rate at which a unit of charge moves through a circuit per unit of time. So it's an amp is pretty much a coulomb per second. The resistance is the amount of traffic or the amount of impedance which these charges have to go through while going through the circuit. So in general, the units are given by ohms, which is given by the capital Greek letter omega. So this symbol right here is going to be what we use to represent a resistor. This symbol right here is what we use to represent a battery in a regular schematic, electrical circuit schematic. So let's actually just go through like a small analogy which kind of demonstrates Ohm's law. So suppose you were to run in a kind of marathon where you're going through just one big track. This is the track where you're going through. Well, in this track though, there's this one area where you're actually having a big pit stop. And at this pit stop, you have pretty much like a big table, which has lots of energy drinks, like Red Bull, etc. Lots of these little energy drinks. And in another part of this track, you have this little obstacle course, which I guess can act like maybe like a big river or maybe like a big quicksand or something of that sort, which you have to go through as well. But this area you would be going through like a much slower rate in comparison. So let's suppose that in this supposed marathon, you have lots of people, but the goal of this marathon is just to keep running around this marathon until the ref pretty much stops you. You would be starting here, just keep going, and you just keep going on and on. And in this little pit stop, these little free energy drinks, you can use those energy drinks whenever you want to pretty much power you through. And this right here is going to be our symbol for, it's like an analogy for the voltage itself. The track pretty much is pretty simple. You can run through it without really getting tired or anything. But at this portion, the little quicksand or maybe the swimming area, which is very difficult for a lot of people, is going to be, or for everyone here, I guess, is going to be the area where you need to use up these energy drinks. And this right here is going to be what we consider to be our resistance. So overall, this entire pathway is going to be a circuit. This is going to be a resistor. This right here is going to be our little voltage, or maybe the battery itself. And the amount of people that go in, these little people are going to be units of charges. The rate at which these units are able to, on average, just go through this entire circuit is going to be represented by the current. All right. So using that, let's try and figure out a few understandings of like how a circuit itself works. So here we have pretty much a very basic schematic of a circuit, pretty identical to the other one that I drew over there. Well, in this circuit, we have a voltage called V1, which has a voltage of 5 volts. And in the circuit, we also have a resistor, R1, which has a total resistance of 10 ohms. If I were to ask you, like, what is the current going through this circuit, we would just be able to use Ohm's law and say that V1 is equal to I times R1. Or since V equals IR, we are able to just say that V1 would equal whatever I is times R1. Well, we already have a value for R1, which is 10 ohms, and we already have a value for V1, which is 5 volts. So this would mean that we have a total of 5 volts here, which is equal to, and actually if we just divide, if we re-represent this, we can just use that V over R is equal to the current. The same thing as saying one or the other. So using this, we're able to just say that V1, which is 5 volts, divided by R1, which is 10 volts, 10 ohms, gets you a total current, volts and ohms, gets you a total current of 0.5 amps. So on average, currents going through this, they're all going to be moving at a rate of 0.5 coulombs per second. So through the circuit, 0.5 charges would be going every single second. All right, let's try to make this graph a little bit more complex. So we still have the same voltages, but now let's add an extra resistor. So let's say that our new diagram looks very similar to the last one, but now we have a second resistor. The second resistor is R2. Well, in order to find the total current that's going through the circuit, you can think about, well, what if I were to just add an extra obstacle right about here? Well, overall, that's just going to slow down the entire process even more. So the overall current would just be even further reduced. And this is what we call a series circuit. So whenever you have multiple resistors back to back inside of a circuit, this is what we call a series circuit, where they're arranged in such a way that you have to cross through both of them. Well, and the total resistance that you would be going through is going to be RT is equal to the resistance of the first one plus the resistance of the second one. Well, in this case, that's just equal to 10 ohms plus 20 ohms, which means our total resistance is equal to 30 ohms. And we get that our voltage, which is 5 volts, and if we divide by 30 ohms, which is the total resistance, we get a total current on average, which goes through both of these resistors. All electrons here are going to be going in at the same exact rate of 0.1667 1666 or 167 amps. Right. Now let's suppose that we change this diagram even further. Let's say that we change this diagram to be more so even further complicated, where we have our first resistor right here, but we also have a second resistor right about here, which is called R2. So in this case, we have electrons, or we have current, which is passing through in this direction, but the current can stop right here and think about, okay, do I want to go through this path, or do I want to go through this other path? Either path would work. So if you're thinking about maybe like cars, or maybe in this case, another way to think about this is if I were to just add an extra obstacle course right about here. Well, if people just want to go finish the entire line, even if this one right here is probably harder, if there's a lot of people here, people are likely to go through here as well. So that kind of just speeds up the overall process. So in general, whenever you this is what we call two resistors in parallel. And whenever you have multiple resistors in a position where you can go through both of them, you don't have to go through both of them, but you can just choose which one you want to go through. That's when you have a parallel circuit. So the total resistance inside of a parallel circuit is R total. 1 over R total is equal to 1 over R1 plus 1 over R2. All right. So in this case, 1 over R total, which is what we're looking for right now, is equal to 1 over R2, or 1 over R1, which is 1 over 10, plus 1 over 20. So 1 over 20, 1 over 10 plus 1 over 20, that's equal to 0.15. And 1 over RT is equal to this, which indicates that RT is equal to 6.67 ohms. 6.67 ohms is even smaller than both R1 and R2. So the total resistance of this entire circuit is even smaller than if you were to just have R1 by itself. The reason behind that is because you're able to choose, do you want to go through R1 or do you want to go through R2? Either one works. So in general, people would be going through R2. Like if you were to have that obstacle course, if it's the case of the current and stuff, the charges would want to go through R1, not R2. But when it sees like many charges just like piling up over here, it would immediately choose, okay, I might as well just go through R2, even though it's like slightly more resistive. There's less here, so might as well just go through that path. Now, if you were to find the current though, you would be able to use the same exact process, and we would be able to get that the current in this diagram, the current here, right about here, is the same as the current here. So this is I, and this is I. Same exact current. And that's equal to the total current of the system. And to do that, we just do whatever the voltage is divided by the total resistance, which is V1 divided by, or V1, which is 5, divided by 5 volts over 6.67 ohms. And this gets you roughly this gets you 0.75 amps. However, this current is not exactly the same for both of these resistors though. So both of these resistors have their own separate current. Because these like charges are going through these resistors from two different locations, and these resistances have two different levels of resistance, the current that passes through it is going to be different. So here we're going to have a current of 5 volts divided by the resistance here, which is 5 divided by 10, or 0.5 amps. Here we're going to have a total current of 5 volts divided by 20 ohms, which gets you 0.25 amps. Now the reason as to why we're able to use the same 5 volts and we're able to get like different values of currents is a result of two laws by a man named Kirchhoff, which demonstrates how current itself travels through a circuit. So Kirchhoff's first law, not just current, also how voltage works as well. So the first law is Kirchhoff's current law, or KCL. Well, this simply states that the current that enters a junction is going to be the same as the current that leaves a junction. The sum of the currents that enter a junction is the same as the sum of the currents that leave the junction. So we start with the current, which is I, or 0.75 amps, right about here. Now, at this junction, these charges are just moving around at two different rates. Here, they would be moving at a rate of 0.5 amps, and here they would be moving at 0.25 amps. Adding them together, we get 0.75 amps. Now, once again, they reach another junction where both of them meet together again. Now, once again, they add up to being 0.75 amps. Now, there's Kirchhoff's second law as well, or Kirchhoff's second law, which is his voltage law. So according to Kirchhoff's second law, the total potential difference, which is going to be the voltage pretty much by whatever the battery it is that you're using, is going to be the same as the sum of all the voltage drops that exist. So if this was just a single circuit, we would be able to just say that the total potential difference is the same as the voltage drop, which happens at this one resistor right here. So the voltage drop is the same in overall. However, when it comes to being two resistances, we have it so that the total voltage difference is actually the same in both cases. The reasoning behind that is because according to the Kirchhoff's first law, we have that the current is already the same. And now using that, we're able to go back to saying, okay, as a result, the voltages here has to be the same as well. So in parallel circuits, the currents here and here are going to be different because of KCL. But in a series circuit, let's say you would draw an extra resistor right there, the voltage would actually be different. There's a voltage drop for here, and there's a separate voltage drop here. But the current would be exactly constant. Now let's suppose that you have multiple batteries in this case. Let's ignore the second resistor actually. All right, so now let's suppose that we're getting rid of the second resistor and we're looking at it so that we have two batteries. So we edit this entire circuit so that we have two batteries. Let's say we have a V1 here. Let's draw the circuit first. So we have just one resistor this time and two batteries. Let's say this is R2 and this is V1 and V2. So V1 has a voltage of 5 volts and V2 has a voltage of 15 volts, R2 has a resistance of 20 ohms. Well, in this case, the total voltage here would actually be the summation of both of these batteries. It would actually be just 5 plus 15, 20 volts. And you can kind of like draw like a bigger battery just out of this, pretty much like a bigger battery out of it, which is just equal to V1 plus V2. However, now let's reorient this so that the circuit looks slightly different. Let's say that V1 were to actually V2 were to look something like this, and V1 were to look something like this, and you had a resistor right here, and that. Imagine this to be a little bit closer actually, but still. Anyway, I guess you could just draw a wire right here as well, but it doesn't really matter. In this case, you may notice that the only difference that I actually drew here is that the orientation of the long bar and the short bar is just slightly different. Here, I mean, in the past one, it was something like, actually, they were both in the same direction. In this one, they're both in opposite direction. When they're in opposing directions, this means that the current flows this way from one side and in the exact opposite way from the other side, which means that their voltages start to cancel each other out. So V2 would be 15 volts, V1, which is 5 volts. Both of these would start canceling each other out, and in total, you would get a total voltage of 10 volts. In the past example, we had 20 volts, whereas in this example, we'd be getting 10 volts. And the 10 volts would be the current that's going in this direction. Now, how do we determine which direction does the current go through? All right. The way to determine which direction current follows is by pretty much just looking at wherever the big bar is. The big bar represents the conventional flow of current, and you would follow from the big bar and go down to the smaller bar. So in a general battery, in general circuit, you would go up, resistor, and then back to the small bar. However, this represents the positive terminal and this represents the negative terminal of battery, and this kind of shows like the representation of a positive charge moving through a circuit, but in real life, it's the electrons that does the traveling. So in real life, the circuit actually follows in a direction kind of like that, whereas by convention, it goes in this direction. All right, that's about it for this video. Thanks for watching. Have a good day.